Welcome to They Deep Dive. Today we're jumping right into, well, the heart of our energy future. The whole global energy scene is shifting, right, towards clean renewables. And behind all that are these sophisticated power electronic converters, kind of the unsung heroes. We're focusing on grid-forming converters. They're essential for weaving solar and wind into our grids. But there's a catch. As we add more, keeping the grid stable, especially when things go wrong, gets harder.
That's exactly right. The core challenge is that these new converters, they're super efficient, but also, well, sensitive. Your traditional power plants, the big synchronous generators, they can take huge electrical hits. We're talking maybe 7 times their normal current.
7 times. Wow.
Yeah, they just power through.
Yeah.
But these new converters, they're more like finely tuned instruments. They can only handle a tiny overload, maybe 20%.
Just 20%.
Yeah, 20%.
Yeah.
So they really need advanced controls to shield themselves from big problems, short circuits, voltage drops, things like that. And crucially, they have to do this while staying locked in sync with the whole power system.
Okay, so protect the delicate hardware, but don't destabilize the grid in the process. Sounds tricky.
It is a real balancing act.
So our deep dive today, it's about a really fascinating discovery, something that boosts the resilience of these converters. We're looking at one specific protection method, the current saturation algorithm, or CSA, and our mission to show how this previously overlooked angle actually makes a huge difference.
Exactly. Because while these current limiting strategies like CSA are vital for protection, they can sometimes backfire. They can actually hurt what we call transient stability.
Transient stability. Okay, help me out. That's like...
Think of it like the grid's ability to recover its balance after a big shove. A sudden fault, for instance. If you can't regain balance quickly, you risk wider problems, maybe even blackouts. This paper we're looking at investigates the impact of one specific variable in the CSA, the current reference angle. They call it phi.
Right, phi. And this is where it gets really interesting, you said.
It does. Because this phi, it wasn't just seen as a parameter. They realized it's a whole new control lever, a new degree of freedom they could use.
A hidden control knob, basically.
Sort of, yeah. They figured out how changing phi affects stability and even derived formulas for key metrics, like the critical clearing time, CCT. That's essentially the maximum time a fault can last before the system becomes unstable.
So finding the right phi lets the system ride out problems for longer.
Precisely. They found you can calculate an optimal phi. This optimal setting significantly boosts stability. It lets the converter handle disturbances for longer. And importantly, it also helps the converter smoothly return to its normal operation, controlling voltage, once the fault is cleared. That seamless transition is key.
That makes sense. So what kind of real-world disturbances are we talking about? How does phi help in practice?
Well, they tested against common grid events, things like balanced voltage sags, sudden drops in voltage. It even showed benefits during 100% sag, which is basically a temporary complete loss of voltage at that point.
Wow, even a total voltage loss.
Yes, and also for phase shifts. These can happen when, say, a transmission line is switched back in after maintenance or a fault. It can jolt the system's rhythm.
Okay, voltage sags and phase shifts.
And here's the surprising part. The research showed phi actually had an even stronger positive effect during a phase shift compared to a voltage sag.
Really? Why is that?
It boils down to how phi helps manage something called the power angle deviation. Imagine all the generators and converters needing to stay in step, like dancers. A disturbance tries to push them out of sync. That deviation is the power angle. Phi helps control that deviation more effectively during phase shifts, keeping everything synchronized.
So let's wrap this up. What's the big takeaway here?
It means that adjusting this one angle, this phi, which might seem like a small technical detail, it can unlock significant improvements in how robust and stable our power grids are.
Especially crucial now with all the renewables coming online.
Absolutely.
Yeah.
It really underlines how vital it is to understand the deep, sometimes subtle interactions within these complex systems.
Finding those critical little details.
Exactly. It's often those overlooked details that ensure our advanced tech works reliably, not just efficiently. Keeping the lights on, fundamentally.
It's a great insight. And it leaves me thinking, maybe leaves you thinking too, what other hidden knobs or settings might be out there in all sorts of complex systems around us, technology, biology, maybe even finance. Parameters just waiting to be understood to unlock better performance, more resilience, something to ponder. That's it for this deep dive. Thanks for joining us.